In this video, I'm going to be showing you guys how to find the critical angle for a projectile. This is the question, and it is basically asking us to find that critical angle. So, whenever we throw projectiles, the projectiles usually keep on increasing in distance from the origin. So this being the origin, O, let's just say first the distance is this much, and then we see that the distance is keeps on increasing, right? But when we throw the projectile at a much larger angle, we realize that the distance is maximum at a point, and then afterwards it's decreasing. We see that this line here, we see that this line here is shorter than this line or any of these lines. See, now this begs the question, at what angle theta shall we throw the projectile such that the distance from the origin will go on increasing from a certain point. So it will go on decreasing from a certain point instead of increasing. That angle is called the critical angle, and it is a relatively large angle, since we realize that whenever the throw is usually steep, we can see that the distance goes on increasing, versus usually when the angle is smaller, the distance keeps on increasing. So that's pretty much the concept behind the projectile's critical angle. And now we will go on to finding. Let's make an equation. The distance from origin, we'll say, is DO, can be written as DO equals the distance from the x-axis squared plus the distance from the y-axis squared under a root. Now, we know how to find the distance from the x and y axes relatively easily. We know that dx equals, which is basically the distance covered in the x-axis by the projectile, is the projectile's velocity in the x direction times the time it has traveled for. And dy from ut equals ut plus half at squared is going to be uyt plus half at squared. Now, since for dy uyt is, we write uyt as is, and since acceleration is negative g, we just write minus half gt squared. Now dx is going to be uxt, which is simply u cos theta t. Dy is going to be uyt minus half gt squared, which is u sin theta t minus half gt squared. Now that we have this expression, we can go ahead doing our further calculations from it. So the distance from the origin can be written as dx squared plus dy squared, which simply, let's just square in both sides. We're going to treat it as distance from origin squared is just going to be distance from x squared plus distance from y squared equals u sin theta t squared minus u cos theta t squared minus u sin theta plus u sin theta minus half gt squared whole squared. Now this leaves us an expression u squared cos squared theta t squared, which we get from this, and this leaves us the expression u squared sin squared theta t squared minus 2 times u sin theta t times half gt squared, and this leaves us the last expression squared is simply 1 over 4 g squared t to the power 4. Now u squared and t squared can be taken common from these expressions. So u squared t squared common, and then we get cos squared theta plus sin squared theta, which is just 1, minus here in the other expression, this one, what we can simply do is we can chop the 2's. So we just cut the 2's here, and then we're left with u sin theta gt cubed plus here the last expression remains as is. And now we have the distance from the origin squared to be this value. So the distance from the origin is just going to be root under u squared t squared minus u sine theta gt cubed plus 1/4 g squared t to the power 4. Now, to find whether the distance from the origin is increasing or decreasing, we use what we learned when we studied increasing and decreasing functions. So we know that a function is increasing when function's first derivative is positive, when the is positive, and decreasing when function first derivative is negative. Now, since we have these values, we can also know what a stationary point means. A stationary point is the point that distinguishes when a function is increasing, which is in this part, and decreasing, which is in this part, and this becomes the stationary point. Now, the stationary point will satisfy the equation the function's first derivative equals 0. So, the existence of the stationary point alone will prove that a function after a certain point goes on decreasing. So that is the significance of the stationary point here. So let's just take the distance from the origins and let's just differentiate it with respect to time. So differentiating distance from origin with respect to time, we are left with a wonderful expression which we will only get after doing a gruesome, not really gruesome, but tedious differentiation. We have to differentiate roots. U squared, which is u squared t squared minus u sine theta gt squared, gt cubed, I think, gt cubed, yes, plus 1 over 4 g squared t to the power 4. Now, you can differentiate the roots, which is no problem, but since it's a bit tedious, you can also, instead of differentiating the distance from the origin, you can differentiate the distance from the origin squared, which really does not make the expression any less different in regards to the problem that we're solving, but really makes the calculations easier because you don't have to differentiate the root. So I just removed the root right there. I'm going to remove it again so you guys know now. We can just remove this root if we just, instead of differentiating the distance from the origin, we differentiate the distance from the origin squared. So now we don't have to differentiate the roots. Now differentiating this value for 0, right? We're going to first differentiate and then we're going to solve it for t equals 0. Now differentiating it gives us what? It gives us, the first expression comes out to be 2u squared t. The second comes out to be 3u sine theta gt squared. And the third comes out to be g squared t squared. No, sorry, g squared t cubed. Now, solving for 0. Let's solve it for 0 since we're trying to get the stationary point. U squared t squared minus 3u sine theta gt squared plus g squared t cubed equals 0. We realize that we can initially take t common. And then we have a potential solution of t equals 0. And the other solution is 2u squared minus 3u sine theta gt plus g squared t squared equals 0. Now is when the most beautiful part comes in. Now we have a quadratic equation for the second expression. The second expression is 2u squared minus 3u sine theta gt plus g squared t squared equals 0. And this quadratic is in the quadratic of t squared. So when we compare it with ax squared plus bx plus c, we see that x squared is t squared and x is t. So x is simply t. And the constant here is 2u squared. Now, the intuition behind what we're going to do now is we need to realize that time here, the solution for time, the solution for time is going to be always a real number. And for this to give a real number solution, the discriminant, yes, the discriminant d has to be always either 0 or greater than 0, which is simply a positive number. So I hope you guys understood that. Let me go ahead and repeat it once more time. The solution for t here is always going to be a real number, and for this to have a real number solution, the discriminant always has to be positive. So solving for the positive of the discriminant, we realize that b here is negative 3u sine theta g, a here is 2u squared, and c here is, sorry, a here is g squared and c is 2u squared. Now solving for d equals 0, we get that b squared minus 4ac has to be greater or equals to 0, or b squared has to be greater or equal to 4ac. Now b squared is simply 9u squared sine squared theta g squared from this expression, and 4ac is just going to be 4 times this time this and this, so it's just going to be 8 u squared g squared. Now we chop g squared u squared, which leaves us with an amazing and beautiful expression of sine squared theta is greater or equal to 8 over 9, and sine of theta is greater or equal to root of 8 over 9, or theta has to be greater or equal to sine inverse root 8 over 9, then theta comes out to be approximately 70.1 degrees. And this 70.1 degrees is the critical angle. How exciting!